Okay, let's dive right in. Today, we are looking at a technology that could completely rewire one of the world's biggest and oldest industries. We're talking about making steel, but without any carbon. We're talking about iron electrolysis. I want to start with just one number, 1.9 tons. That right there is how much carbon dioxide gets pumped into the atmosphere for every single ton of steel made the old-fashioned way. It's a staggering figure, and it's the fundamental problem we're trying to solve today.
You know, for centuries, the recipe for making iron has been pretty much the same. You take iron ore, you blast it with massive amounts of coal and coke at absolutely scorching temperatures. And look, it works. But that process is responsible for a huge slice of global emissions. So the question is, can we finally break that chain?
So here's our game plan. We'll start with the problem, then get into the core science of what electrolysis even is. We'll compare the different ways to do it, hot versus cold. We'll look at the brutal engineering hurdles, see how it stacks up against its main rival, hydrogen, and then finish up with the big picture, the race for green steel.
Our modern world is literally built with steel, but making it comes with an environmental price tag that is just becoming too high to pay. So, how do we fix it?
And that brings us to the potential solution, iron electrolysis. The idea itself is actually brilliantly simple. Instead of using carbon to rip oxygen away from iron ore, you just use electricity to do the job. The only thing that comes out the other end is pure iron and pure oxygen. That's it, no CO2.
So, how does it actually work? Well, it really boils down to three key steps. First, you have to dissolve your iron ore in a special liquid called an electrolyte, something that can conduct electricity. Second, you run a current through that liquid. And third, that electricity works its magic. It splits the ore, pure iron collects on one side, and pure oxygen just bubbles up on the other.
And look, this isn't some pie-in-the-sky science fiction. We already do this at a massive scale. As this quote points out, 100% of the world's primary aluminum is made using this exact same principle. The chemistry is proven. The real challenge, the hard part, is adapting this to the much more brutal conditions you need for making iron.
Right, so how do you handle those brutal conditions? This is where the competition really heats up, literally. It all comes down to a battle of temperatures. You've basically got two main camps, hot electrolysis and cold electrolysis.
This table lays out the whole trade-off. You can go cold, around 110 degrees Celsius, and you get an efficient process. But the big hurdle is that it's tough to dissolve enough iron ore to make it work at a massive scale. Or you can go absolutely volcanic, we're talking 1600 degrees, and produce liquid iron directly. The catch, you have to find materials that can survive inside what is essentially man-made lava.
Let's zoom in on the low-temp approach for a second. The best way to think about it is like electroplating, just on a huge industrial scale. Its biggest superpower is flexibility. Because it runs relatively cool, you can turn the process on and off pretty easily, and that is a game changer, because it means you can perfectly sync up with cheap but intermittent renewable power, like when the sun is shining or the wind is blowing.
And here's the other end of the spectrum. This is a pilot cell for high-temperature electrolysis. The goal here is pure ambition. Produce liquid iron directly, ready to go, skipping several steps. The upside is a simpler, more streamlined process. The engineering challenge, though, is immense. You're trying to build a box to hold a corrosive 1600-degree molten bath that is actively trying to destroy the box it's in.
Which brings us to what I call the industrial gauntlet. Because it doesn't matter if you go hot or cold. Every single one of these electrolysis methods has to face a common set of really formidable challenges if it's ever going to get from a cool lab experiment to a reliable industrial-scale factory.
The basic principle works, we know that, but industrial reality is just unforgiving. It's a material science nightmare. The single biggest problem is the anode problem. The anode is where all that oxygen gets produced, but in these conditions, that high current corrosive reaction is literally eating the anode alive. Finding a material that is durable, conductive, and can survive that is the holy grail. And that's on top of building the whole reactor to withstand the stress and managing the molten goo so gas bubbles can actually escape. Okay, so let's pull the camera back a little bit. Electrolysis isn't the only horse in this race. Its biggest rival for making green steel is a process that uses hydrogen. So how do they actually stack up against each other?
So here's the showdown. On one side, you have direct electrolysis. It's the elegant solution. It's more efficient on paper because you're using electrons directly. But the tech is just less mature. It has these massive material science problems that nobody has solved yet. On the other side, you have hydrogen. It's the more straightforward path because they can adapt infrastructure that already exists. But it comes with its own huge baggage. You need a colossal, expensive new system to produce, store, and transport all that hydrogen.
So this all leads us to our final section, the race for green steel. What's the ultimate potential here, and what does the path forward actually look like?
And this right here, this is the prize. If, and believe me, it is a huge if, these engineering challenges can be solved, iron electrolysis could wipe out nearly all of the CO2 emissions from making new steel. We're not talking about a small improvement. This is a near total transformation of one of the planet's most polluting industries.
But the verdict for now is crystal clear. There is no single winner yet. The entire future of green steel really boils down to this one crucial trade-off. Do you bet on the more elegant, more efficient path of direct electrolysis, knowing you have to solve these epic materials and scaling problems? Or do you go with the more mature hydrogen tech and just accept the massive infrastructure bill that comes with it?
And so that's the question we're left with. The science, the principle of using electrolysis to make iron, that's not in doubt. It works. The real race is about engineering and economics. Which one of these technologies is going to be the first to crack the code of industrial durability, competitive cost, and just mind-boggling scale? The answer is going to define the future of the single most important building material in the world.